Hello, everyone, and thanks for joining. I'm going to give it a few more minutes to see if we have any additional participants before we get started. Okay, it looks like no one's logged in a little while, so we'll go ahead and get, oh, we just got one more. Sorry, I'm too fast. We'll get going here in a second anyway, though. My name is Aaron Prater. I'll be your MC for today, and welcome back to Gaining Ground. Gaining Ground webinar series is based upon work supported by the National Institute of Food and Agriculture and the U.S. Department of Agriculture. And about this series, it's organized by the Urban Food Systems graduate student cohort, and it's designed to provide agriculture educators with tools and skills to better support urban food system enterprises. Topics focus on financing, business management, and marketing, and it's funded by North Central SARE's PDP grant under a project titled Capacity Building in Urban Food Systems in North Central Region. So with those introductions aside, we're going to get to our guest speaker today. Our topic is aquaculture and hydroponics and sustainable foods futures. And our guest is Dr. Nikolaos Katsoulas, from a professor at the University of Thessaly. He's going to talk to us about aquaculture and hydroponics. Please put your questions in the Q&A box, and we'll get to them. We'll have a Q&A session at the end of Dr. Katsoulas' presentation. And without further ado, I am going to turn off my camera and pass it over to you, Dr. Katsoulas. Thank you.
Thank you very much, and thank you for joining. First of all, for inviting me to this seminar, to this webinar. Let me share my screen as soon as you end sharing your screen, so that I can show you my slides and presentation. Okay, I hope this is fine for you and that you can see my screen. So, as introduced, my name is Nikolaos Katsoulas, and I'm coming from the University of Thessaly, that is in central Greece. And I'm professor here at this university and director of the Lab of Agricultural Constructions and Environmental Control of the University of Thessaly. But I'm going to talk about the activities that we have in the pilot circular economy greenhouse park at the University of Thessaly at Velestino, where we will see aquaponics, hydroponics, and sustainable food production systems for future. So let's just see where we are. I hope that I have pinned correctly your location here, and we are at the center of Greece, in this place here. So we are far away, but I hope that we will have that you will enjoy this presentation today. So a few words about the University of Thessaly that I'm located. The University of Thessaly has 35 departments, and one of these departments is the Department of Agriculture, Crop Production and Rural Environment. And of course, at the School of Agricultural Sciences, there are 4 more departments, so 5 departments in the school. The Department of Agriculture has 20 laboratories for different disciplines, different subjects, and one of these laboratories is the Laboratory of Agricultural Constructions and Environmental Control that I'm leading in this department. Except me, that I'm the only permanent person in the group. There are several people working as researchers in different kind of projects that we will see later on, and 2-3 colleagues that are also working at the University of Thessaly in other departments and that we are collaborating. So we are quite big group for the known things, let's say, at the different laboratories at the university, with a lot of activity in different projects. As I said at the beginning, we are trying to incorporate the circular economy concept in our activities. That is, in a circular economy, the value of products and materials is maintained as long as possible, and waste and resources used are minimized and resources are kept within the economy when a product has reached the end of its life, to be used again and again to create further value. A circular economy is a regenerative system in which resources, input and waste emissions and energy leakage are minimized by slowing, closing and narrowing material and energy loops. This can be achieved through long-lasting design, maintenance, reducing, alternatively reusing, recycling and recovering materials. This is in contrast to a linear economy, which is a take, make, dispose model of production. The term encompasses more than the production and consumption of goods and services, including a shift from fossil fuels to the use of renewable energy and the role of diversity as a characteristic of resilient and productive systems. It includes discussion of the role of money and finance as part of the wider debate, and some of its pioneers have called for a revamp of economic performance measurement tools. It needs, of course, novel business models and responsible consumers. Thus, the promotion of consumer responsibility is crucial for circular economy. Probably organic farming is among the systems that is very close in this concept of circular economy, since it has many closed loops in its performance. So a circular economy is restorative and regenerative by design and aims to keep products, components, and materials at their highest utility and value at all times, a concept that distinguishes between technical and biological cycles. The circular economy is a continuous positive development cycle. It preserves and enhances natural capital, optimizes resources yields, and minimizes system risk by managing finite stocks and renewable flows. And of course, a circular economy works effectively at every scale. So during this presentation, we will see how a cascade system, that is a small loop here in a circular economy system, or a bigger loop system, an aquaponic system, is working. There is a high need for circularity in horticulture, and there is a group, a focus group in Europe that discussed a lot about circularity in horticulture. The agricultural sector plays a significant role to the world economy, as 40% of the global population earns its livelihood through it. Aided by the issues of malnutrition and food insecurity, food production and distribution on a global scale is very important. We expect that the population increase during the next 20-30 years will lead to an increase in the need for food production of about 70%. So we have to produce more food, and we have to produce more food when energy, land, water have to be limited or are already limited. We have to use less resources in order to produce more food. And of course, we have also the effect of climate change. So greenhouses are one of the means to produce more with less inputs. And the reasons of why we need to cultivate in greenhouses are shown here. We can have out of season year-round production, higher productivity per unit soil surface, more reliable production that is less affected by outside climate conditions, and the higher the technology that is used in the greenhouse, the less the effect of outside climate. High technological greenhouses have less effect from outside climate conditions. Of course, in greenhouses, we have improved control of pests and diseases, and of course, higher quality, uniformity of production. This is due to the better control that we have from temperature, light, humidity, and CO2 in the greenhouses, and of course, better irrigation, fertilization, and better control of pests and fungi in the greenhouse. And you see here some figures in relation to the kilograms of fresh product that is produced per cubic meter of water. In open field, that we have about 3 kilograms of peppers, let's say, per cubic meter of water, and 43 kilograms in a modern high-tech greenhouse. Something also relevant is shown here. For 1 kilogram of tomato, based on data that we have from different regions around the world, for a high-tech greenhouse that is in the Netherlands, we need about 4 liters of water, while in the open field, in order to produce 1 kilogram of tomato, we need about 60 liters of water. Of course, there is a big difference between these two values, and there are greenhouses with values between these two, of course, numbers, depending on the technology that is used in each greenhouse. So we will see some projects that we are running at the University of Thessaly, and where we are trying to incorporate this circular economy concept. And of course, we are trying to reduce the use of inputs and to reduce the leakage of outputs from the greenhouse, like water and nutrients, for example, so that the environmental impact of the greenhouse production system is minimized. First of all, we'll see a cascade hydroponic system, then the aquaponic system, and a few words about the microalgae production system and the greenhouse and the project related to reduction of pesticides and fertilizers in the greenhouses. But before we see more details about the projects, I would like to present you a video where we can see the greenhouse park at Velestino that we can see here. It's a high-tech greenhouse of around 1,500 square meters, and an aquaponic greenhouse here, and 3 smaller lower tech greenhouses in the other around these new greenhouses. And I hope that you will also see the subtitles here. Can you confirm that the sound is coming to you?
Βρισκόμαστε στα θερμοκήπια του Πανεπιστημίου Θεσσαλίας, στο αγρόκτημα του Πανεπιστημίου Θεσσαλίας στο Βελεστίνο, όπου υλοποιούνται τα περισσότερα ερευνητικά έργα του Εργαστηρίου Γεωργικών Κατασκευών και Ελέγχου Περιβάλλοντος του Πανεπιστημίου Θεσσαλίας. Στα ερευνητικά αυτά έργα, το αντικείμενό τους είναι σχετικό φυσικά με τα θερμοκήπια και στόχο έχουμε την υλοποίηση του σκεπτικού της κυκλικής οικονομίας. Έτσι, σε ένα από τα 10 περίπου ερευνητικά έργα που υλοποιούνται την περίοδο αυτή στα θερμοκήπια, χρησιμοποιούμε τις απορροές που προέρχονται από μία κύρια καλλιέργεια που έχουμε στο θερμοκήπιο για να αρδεύσουμε μία δευτερεύουσα καλλιέργεια που εδώ στην περίπτωσή μας αυτή είναι ο δυόσμος και η μέντα. Έτσι, χρησιμοποιούμε εισρωές οι οποίες προέρχονται από τις απορροές, τις εκροές μιας άλλης χρήσης, μιας άλλης καλλιέργειας και με τον τρόπο αυτό εξοικονομούμε νερό και λιπάσματα. Οι καλλιέργειες γίνονται όλες, στην περίπτωση των θερμοκηπίων μας, σε υδροπονικά συστήματα. Εδώ λοιπόν φαίνεται η κύρια καλλιέργεια που έχουμε την περίοδο αυτή στο θερμοκήπιό μας, η οποία είναι καλλιέργεια ντομάτας και καλλιεργείται σε διαφορετικά υποστρώματα, περλίτη και πετροβάμβακα. Υλοποιούνται έργα που έχουν να κάνουν κυρίως με την διαχείριση του κλίματος του θερμοκηπίου, την ανάπτυξη τέτοιων καινοτόμων συστημάτων για τη διαχείριση του κλίματος και της άρδευσης και λίπανσης στο εσωτερικό του θερμοκηπίου. Έτσι, σε συνεργασία με πολλά ερευνητικά ιδρύματα από την Ελλάδα και το εξωτερικό, με εταιρείες υλοποιούμε έργα τα οποία έχουν στόχο την εξοικονόμηση ενέργειας, την εξοικονόμηση νερού, την εξοικονόμηση λιπασμάτων, προκειμένου να μπορούμε να δώσουμε στον παραγωγό ένα εργαλείο, να δώσουμε γνώσεις οι οποίες θα χρησιμοποιηθούν προς όφελός του, να αυξήσει την παραγωγή του και φυσικά να αυξήσει τα έσοδά του στον χώρο του θερμοκηπίου. Υλοποιούνται έργα που έχουν να κάνουν με την ενυδριοπονία, για παράδειγμα, όπου το νερό που προκύπτει από την ιχθυοκαλλιέργεια χρησιμοποιείται σε μια καλλιέργεια στον χώρο του θερμοκηπίου ως εισρωή, γιατί τα ψάρια μας δίνουν λίπασμα τα οποία μπορούν να χρησιμοποιηθούν στα φυτά μας. Φυσικά, σε όλα αυτά τα έργα εργάζονται αρκετά άτομα και στην ομάδα του Εργαστηρίου Γεωργικών Κατασκευών αυτή τη στιγμή υπάρχουν 15 άτομα τα οποία συνεισφέρουν στο να υλοποιηθούν όλα αυτά τα έργα.
Okay, so I hope that you had a clear view of the video. I will continue with the presentation and start with the cascade hydroponic system that you already saw a few figures from this system. The idea is that in hydroponics, we need to have drainage from each crop. So we have about 30 to 40% drainage. That means we supply to the crop 30 to 40% more water and nutrients than needed. And then this drainage in the open systems that in Greece are most of the systems are open, can lead to the environment, and then we lose 30% of water, but almost 50% of the fertilizers that we supply to the crop. And we can have this system as closed and reuse this drainage in the same crop, but then we have some problems of salinity. When we have high salt concentration in the water, when we have low quality of water, the sodium chloride, for example, is accumulated in the system, and we have high levels of salinity that affect our crop. Thus, the idea was that we take this drainage that is drained from a primary crop that is sensitive to salinity, and we supply this drainage directly to a secondary crop that is less sensitive to salinity. And this drainage contains nutrients that are needed for the development of the secondary crop. And then we have again a third loop where a third crop, a tertiary crop, is used in order to fertigate this crop that is much more less sensitive to salinity. So a primary crop, let's say tomato or cucumber, and then a secondary and a tertiary crop that are not sensitive to salinity. So this is the idea, and we developed such a system in the greenhouse facilities of the University of Thessaly and tested this system. And of course, in order to manage this system, we had to develop also control system for the management of the nutrient solution. And this system, of course, was tested in our facilities. And here we can see a primary tomato crop, a primary crop that is connected to a secondary, and we tested as secondary crops lettuce or spinach. Of course, lettuce is also sensitive to salinity. And we also tested parsley, mint, and mint. And we saw very good results where the secondary and the tertiary crops were not, let's say, used additional water or nutrients, but used just the water and nutrients drained from the primary, from the tomato crop. Thus, we could reduce the needs for water and nutrients. And here we can see a tertiary crop, Chrysanthemum maritimum and Melissa officinalis, that are very tolerant to salinity, crops tolerant to salinity. So we could increase in our system the water and fertilizer use efficiency. And some results are shown here, but I'm not going to point the details here. We could see an increase in the water and nutrient use efficiency. And of course, we developed also a model for the simulation of the system. The model is validated with the data that we collected inside the greenhouse with the different experiments. And the model can predict the nutrients concentration in the three systems, in the primary, secondary, and tertiary crop. And we can use this model for further case studies, for simulations, in order to see how we can incorporate different kinds of different types of crops and increase the water and fertilizer use efficiency in the greenhouse. So another system that we are developing and testing at the University of Thessaly is the Aquaponics system, where we combine the development, the production of fish and crop together. In aquaponics, we take the water from the fish tanks and then circulate it and fertigate with this water the crop that we have inside the greenhouse. And in this way, we clean, let's say, the water that is leaching from the fish tanks. We clean it from nitrogen that is produced from the fishes, and then we can return it to the fish tanks again, so that we close the loop, close the cycle of water use in the greenhouse. You can see some figures from the aquaponic greenhouse here. Here is the place that we grow. We have the fish tanks, and you will see also a view of these fish tanks. The system has a capacity of about 9 cubic meters, and we can grow about 150 kilograms of fish in 3 tanks that you can see here. And of course, the system that is developed here at our facilities needs also a controller, a computer to control all this cycle of water and the connection between the crop and the fish tanks in order to increase the fertilizers and water use efficiency. During this period, we are testing the system. We have done several tests. We are testing the system in a tomato crop for a second time. It's not common to use the system for for fruit crops, let's say, like tomato or cucumber. So we are testing it in our facilities to see how we can deal with it. Usually we have crops like parsley or lettuce, leafy vegetables, for example, that are grown in the greenhouse and are irrigated with the water that is coming from the fish tanks. Of course, this water has not the concentration of nutrients that we need for our crop, the optimal concentration. For a tomato crop, for example, it may has we may take from this water about 30% of the nitrogen that we need in order to grow our tomatoes. So we supply in some treatments that we are applying the rest of the water, the rest of the nutrients that are needed additionally, and we see that there is a synergistic effect of the aquaponic water with the growth of the crop. We see that in the case of a crop that is fertigated with water that is coming from the aquaponic, from the fish tanks, with this water having some additional nutrients in order to reach the optimal level, we have better results from a conventional, let's say, hydroponic system. And this is because we have some bacteria that are grown, some microorganisms that are grown in this water that are have a beneficial effect on the crop. Here are some figures of the control system that we have developed in order to manage, again, this system that is, of course, we need to control many parameters in order to have a good system. And we have tested the system for different kinds of crop, for basil, petroselinum, cucumber, tomato. Here are some of the results with a comparison to classical hydroponic system. And here we can see the yield that we have obtained with an aquaponic system that is taking the water from the fish tanks and adding there some nutrients and fertilizers in order to reach the optimal level to feed the crop. And we see that in this case, we have better results than in the classical hydroponic system. And of course, this leads to higher water and nutrient use efficiency in the greenhouse. We have zero water going out from the greenhouse and the fish tanks. All the water is used for to grow our crop. Another project that we are working at the University of Thessaly is the development of microalgae. And here we want to close again one other loop. We can develop microalgae either by using the leaching from the greenhouse, but the drainage, let's say, from the hydroponic systems. We can take these drainage and then use it as substrate to grow microalgae, and then this microalgae can be used to develop fish feeding. And then we can use this fish feeding to feed our tilapia fishes in the aquaponic system. And in the circular economy concept that we are testing right now, we are also taking as input in the microalgae system the waste that is produced from biogas and biodiesel production systems. So we take their waste and then we feed our microalgae in order to produce microalgae that are then valuable for our closed loop system. And the last project that is running, that started recently, has to do with reduction of fertilizers and pesticides in the greenhouse. And in this project, we are utilizing the hydroponic crop drainage for microalgae production, and we will establish in our facilities a system like this that is shown here to produce microalgae in a closed chamber. And of course, we will test the bio-based fertilizers and bio-based biostimulants that will be produced from the microalgae that will that will be produced in the greenhouses. And we will also have some bio-based pesticides, again coming from microalgae, that will be tested in our facilities, that are the pilot testing facilities of the total project. So except of these, we will also test some portable hydroponic nutrient solution analyzers, and also some robots that will be installed in the greenhouse and move around in order to to detect if there is any disease or insect in the greenhouse, and then spray the bio-based pesticides in targets where exactly is needed to control any disease or insect in the greenhouse. And this will be also connected to a decision support system in order to have a holistic approach in managing the greenhouse and the aquaponic system that we have in our facilities. I have 1-2 more slides, but I think that the time is passing. I will just show the last one.
In the future, green manuring lays will be processed along with manure to form biogas in the new Symbiosis's innovative dry anaerobic digestion facility. The gas will then be used to dry grain, drive tractors, and power the organic bakery planned for the farm. There will also be enough gas left over to be sold as fuel. The residue left over from biogas production is excellent fertilizer. The symbiotic process recycles nutrients, promotes crop growth, and reduces stress on waterways. Grassland farming and organic manuring bind carbon dioxide to the soil, while biogas production replaces energy derived from fossil fuels. The Palopura symbiosis model.
So you see that we are just a small part of a very big system, and we can then have clustering of complete cities or livestock facilities and other industrial having other industrial forms of applications, and we can have a very circular system, a closed system that will be that will lead to a sustainable environment, and of course that will reduce the footprint of our production systems. This is a project that is not running in our case, of course, this Palopura symbiosis, but of course can be applied in many cases around the world. So with this slide, I would like to thank you for following this presentation, and I hope that I did not took much more time than expected.
No, thank you, Dr. Katsoulas. That was fantastic. You guys are doing a lot of really, really cool stuff out there. I do have a couple questions, but if anybody else has questions, please put them in the Q&A box down here so that we can ask Dr. Katsoulas some questions. So the first one is from Rebecca, and she wants to know what types of fish have you found to be best suited for your aquaponics system, and do you have a preferred species of fish?
We are collaborating in this project with the Department of Fisheries, of Ichthyology of the University of Thessaly. So at this step, we are just working in our greenhouse facilities with tilapia. we are not testing different types of fishes at this stage because tilapia is a fish that is very tolerant, and we are trying to see different things that may take our system at the limits. And as soon as we have a very stable, let's say, system, then we will try different kind of fishes that will be more commercial, at least for our case in Greece, because tilapia is not a fish that is preferable here.
Great, thank you. And then Carrie asks, could you talk a little bit more about the biological benefits of aquaponics?
Yes, of course. In an aquaponic system, we have the fishes that are fed, and then we have the production of ammonia, and this ammonia is then transformed through some bacteria to nitrogen. And we have a level of ammonia that is a limit, let's say, for the development of fishes, and this level may be around 1 to 2 millimole per liter. If we are higher than these levels, then these levels are toxic for the plant. So we need a good population, a good community of bacteria inside in our system to grow and transform the ammonia to nitrogen. Then with this nitrogen, we can cover about 20 to 30% of nitrogen needs in tomato crop, for example, or even higher percentage in lettuce or parsley or basil crops, probably close to 80 or 90% of the needs of these crops. Except of the bacteria that we know that are in our system, the bacteria that are transforming ammonia to nitrogen, we do not know what else exactly is growing in the system. And this is something that is a research topic that will grow during the next during the coming years. A lot of people are working on identifying why a crop that is fed by aquaponic water has better performance than a crop that is fed with the same amount of nutrients, but with clean, let's say, water. And this is due to the other microorganisms and probably bacteria that are growing in the system and have a positive effect to the roots probably of our crop and to the nutrients absorption from the crop that is grown in the greenhouse. So it's not exactly well known which is this benefit. It's something that we are trying to work with during the next years, and probably needs a more detailed study at the level of microorganisms.
Thank you. We have another question. I'm interested to know if you were looking at the nutritional quality of the produce you are growing.
We are looking also to the quality, of course, of the products that we are growing. We are looking, for example, at the content of vitamin C or of lycopene for tomato, of easily measured parameters like the total soluble solids or the acidity of the juice of the fruits that are produced. Of course, dry matter is something that we also measure of the products. Except of this, in our laboratory, we do not have the facilities, let's say, to measure other things. Probably, for example, a volume or color of the products is also measured. And we see that in comparison with open field or in comparison with soil grown crops, hydroponic crops have not something to as negative or less, let's say, than these. And in some cases, of course, the quality of hydroponic cucumber, for example, is much higher than the quality of cucumber that is produced on soil.
Another question on one of the slides you skipped, it looked like you were going to comment on plastic waste in agriculture. Do you have more thoughts on that?
Yes. We can, what I wanted to mention there is that we can have clusters to reduce this waste of materials from our production systems. And with these clusters, for example, we could collect all the material that is wasted from a greenhouse, from the covering of the greenhouse, or from the slabs that we are using in order to have the substrate in the greenhouse. And this can be effectively, of course, used for other purposes when recycling. And if someone has a company that is producing plastic again, or greenhouse films, for example, they can effectively collect and reuse this plastic and produce probably other materials, not just greenhouse films. In Greece, we have a big company that is working on this, but unfortunately is located in Crete, unfortunately for us, but is located in Crete, big island in Greece, because there are the 40% of the greenhouses of the greenhouse area in Greece. So they are collecting the used material. Of course, there is a lot of discussion on how easy you can do that, how easily you can collect and reuse this material. But this is a matter of law sometimes, that we can force the growers to collect and not, let's say, just throw away the material that is a waste from the greenhouse. In sometimes, probably 20 years ago, these materials probably were also burned, but this is not happening now, and they are recycled in most of the cases.
Great, thank you. Last question. Oh, no, another one popped up, but a great presentation. What circular systems with aquaponic, hydroponic do you think are most beneficial to very small farms with limited resources? Perhaps even outdoor systems with greenhouse infrastructure or just polytunnels. So what can a small farm do to get involved in aquaponics and hydroponics?
Well, the aquaponics started, let's say, by the FAO in order to have some systems to feed some people that needed in order to produce at the same time fish and vegetables together. And in this case, when we have a small system, an aquaponic system of let's say 1 cubic meter of water or less, about 600 of liters, we can have at the top of this system about 15 or 20 lettuce plants. And this is a very small scale, let's say, aquaponic system. And in 1 cubic meter, you can have probably more than 20-30 kilograms of fish growing in it. But of course, we have to control always the conditions of temperature, of oxygen in this system in order to have good conditions for both the vegetables and the fishes. So a small pump, a small tank, and substrate that can be located above the fish tank can be a very small system. But if we talk about a commercial system and a system that can have a grower in large scale systems, like the systems that we see, at least for hydroponics, where we have large scale greenhouses and we can invest on automations and invest on the control systems, then we need to have more than 1,000 square meters of greenhouse area, let's say, and then more than probably 15 to 20 cubic meters of fish tanks in order to have a sustainable system. Because it's not very easy to control the complete system. You have to control always temperature, pH, oxygen levels in the tanks in order to have the best conditions, the optimal conditions for both crops, for fish and crop, of course. That is why you saw a lot of automations and a lot of control systems in our system in order to have it completely automatic and, of course, controlled also from distance.
Makes sense. Thank you. And then lastly, I was wondering if you have also interests in project activities in wavelength selective greenhouse covers and photovoltaics integrated into greenhouse systems.
Yes, this is another hot topic, let's say. And yesterday, in fact, was the deadline for submitting proposals in European Union for funding for agro photovoltaics, for funding projects for agro photovoltaics. Up to now, as far as I know, in Europe at least, the greenhouses that have photovoltaics integrated in the roof are not used so much for the production of crops below the photovoltaics. They are used in order to produce electricity, but they are not giving so emphasis on the crop production that is in the greenhouse. So now we need to integrate correctly the photovoltaics in the roof and have photovoltaics that are transparent or semi-transparent at least, and have some light coming in the greenhouse, because light is very essential for crop growth, so that we do not compromise the production of a crop that is below the photovoltaics. We have been involved in some projects related to photovoltaics, but we have not yet covered the greenhouse with photovoltaic. We have just tested some modules and see how they are, which is their efficiency in the greenhouse in producing electricity. And we have developed monitoring systems for these, for the parameters of the climate and, of course, of the production of photovoltaic electricity, in order to see how we can optimize these systems. And we hope that we will get some funding in order to install in the roof of the greenhouse photovoltaics that will be semi-transparent. Up to now, the cost of 1 square meter of semi-transparent photovoltaic is around 300 to 400 euros. So it's very expensive to be sustainable, let's say, to set it in a greenhouse, if you need to have a transparent. If you integrate the classic photovoltaic systems, then you have much less light than needed for the crop, and you compromise, of course, the production of the crop inside the greenhouse.
Great, and I think we've got time for one final question, and it also deals with the economics of this. I would like you to talk a little bit about the cost and return on the investment of this kind of system.
If you mean about the aquaponic, do you mean about the aquaponic system?
I think that's what they're referring to, yes.
Okay, yes. To be honest, we developed the system that is very complex in relation to a normal system that someone could invest. And this is because we need to test many things before we get ready to say that this is the system that we have to apply in your greenhouse, in your aquaponic system. And several companies have approached us to discuss about this question about the sustainability and the economics. We are not ready yet to reply, at least from our team. We need more data and, of course, a system that will be suggested for a grower will be much simpler than the system that we have developed. And will be, of course, a suggestion to be sustainable, economically sustainable, because we believe in this system and we think that it's a solution to save water and nutrients in a greenhouse and produce with lower footprint. That is something that we need to do in the future in order to have more sustainable production systems. So we believe that we will have a sustainable system, but we are not yet ready to say which exactly is the sustainability that we have seen.
Great, thank you so much. I really appreciate your time and all your information and sharing with us. It's a really fascinating subject, and I know there's a lot of interest in it. Just to let everyone else know, this lecture talk has been recorded and will be posted on our Urban Food Systems YouTube channel for viewing later if anybody wants some more information. So thank you so much, Dr. Katsoulas, from all of the students in the Urban Food System and the faculty and all of our guests. Thank you so much for your time today.
Thank you very much for inviting me in this webinar.
And then lastly, we would like to thank Kansas State University's Horticulture and Natural Resource Department, obviously the Urban Food Systems, and the North Central SARE PDP. Please look forward to information coming out about our next webinar series that should be coming soon. And thank you everyone for coming. I really appreciate it.